Hello all and welcome back. So in this video, let's continue our discussion on time complexity and understand how exactly are we going to think about time complexity for a given code. So let's get started. Now before we move forward, we have actually worked and understood few points which I'm going to reiterate and now also explain you using few tools. So the very first one was that we want to evaluate time complexity when our input is very large. Right, so this is something which we have already seen based on the bubble sort code. Now I'm going to show you this with respect to that how and why this exact is the reason, like how the lower input basically gets diminished. The second thing is that we want to calculate for worst test case or worst test input, right? That is the second thing. The third point is that we want to look for largest factor. Now this is something which I would like to actually explain you visually so that you are able to understand the same as well. So let us go to one of the notebooks which I have created, in which we will be diving a little deep into the bubble sort analysis. So pay attention everyone. This is understanding time complexity with bubble sort. Now I'm making sure that I actually build your intuition behind time complexity instead of asking you to remember anything. Okay. So please be a lot attentive because this understanding is going to help you a lot throughout your DSA journey, right? So what I'm doing is again the same thing, importing time, then numpy matplotlib. So this time I am actually trying to just, along with measuring the time, I am just making sure that I also plot it on a graph. So let me run this. Based on the input which we are giving, which is the input sizes of this arrays and the time which our whole algorithm is going to take, we will be actually kind of getting a graph. Right now we have already seen that it can take a little bit time for bubble sort to run. So let it run once, everyone. Now this is actually the kind of relation which we are getting, if you will see. Now in this, we will notice that this is the time taking in nanoseconds and this is the input size. And we are kind of getting this graph, right? Now, one thing to understand here is that we cannot again say that, okay, this much is always the time taken. This is just kind of a graph which we are attaining. And I feel that this graph is a lot equivalent to how we have a graph for n square. Right, so it is kind of increasing with that how when the input size is increasing, I see that the time taking is not increasing linearly, at least it is increasing in some squared manner, right? So with that understanding, what I want to showcase to you is that let's say our bubble sort is having some relation, okay, let's say n square plus n, maybe something like this is the relation where n is your input size. Okay, so this is just something which I am assuming. Again, I'm not saying that this is the exact relation which bubble sort gives us. I want to show you or actually prove you that this particular terms, they are not going to actually have any effect for very large inputs. Now mathematically, I can say that if let's say n is 1 billion, right? Then of course 10 to the power 18 will be a lot large than 10 to the power 9, right? With that in mind, of course, you can understand that how this whole term, this small 10, they will not have an effect. But now let me help you to visualize this as well, right? So that you understand the same thing. You will be getting this notebook, so make sure that you download this. Now what I've done here, let me just run it for 4 maybe. This is n squared, which is n to the power 2. Then this is n squared plus n, right? In a similar manner, n squared plus n. I'm just plotting this value from 1 to 4. So let me just run this code once and see. This is the result we are getting. So for a very small input from 1 to 3 when it is going, what exactly is happening is that n square plus n, this particular thing of course is a little bigger than my n square, and which I think is even understandable as well, right? For example, when n is equals to 1 for a very small input, 1 square plus 1 is going to be 2, whereas 1 square is going to be 1 only, right? So yes, there will be a difference when the input we are talking is small. Okay, but something which we have already conceptualized is that we will always be working on a large input. So let me just run it for 1:10 and let us see the input now. Now you will see that as we go forward, the overall gap seems to be actually getting diminished, right? Because for example, let's say when n is 9, it's exactly equal to 81 and 9 square plus 9, which is going to be 90. Okay, so this gap will actually keep on diminishing. Now let me run it for 40. At 40, you will see that now these two values, they are actually trying to come a lot over one another. The reason for that again is the same. Let's say if I take it for 40, then it's going to be 40 square is going to be 1600 and 40 square plus 40 is going to be 1640. So a very less difference, right? When we see with this respect to this scale, it's a very minor difference. Now the same thing when I run for 400, you will see that the graph will actually be exactly same, right? And I hope you understand the reason for that. N square term is anyway going to dominate and 400 is still very less input. If I'm talking in terms of, let's say, millions or even billions, on which we actually assume n to be a very, very large value, anything which is actually after my most dominating term, that will not have an effect. With that in mind, what I can say also is that if in my code, one thing is there which is taking the major time. Let's say if I have, for example, in my code currently, I have the merge sort and bubble sort both are happening. Then for a very, very large input, okay, again, I'm talking about a very large input. You can think even in terms of multiple billions as well. You can take n as large as possible. The time which will be taken by bubble sort is anyway going to be a lot large than my merge sort. Because we have seen that how slow bubble sort is as compared to merge sort. So all the other values, all the other delays will actually not have an effect. And that is something which I want all of you to understand with this code. Now again, we can see this for, let's say, n square plus 100n when I'm taking 100n as well. Okay, so instead of just n equal to simple n, let us take it 100 and let us try to run this now as well. Okay, so for 10, of course, you will see that, okay, there is a lot of difference, right? So this is another example just I'm taking. So n square, but this time what I've done is, because many students might feel that for a very large n, maybe it have an effect, right? If we have a very large thing here. Well, that will not have. Okay, that is something because we are taking n to be a lot large. Okay, so for n square plus 100, and of course, initially there is a lot of difference. Now when I run it till 100, the difference is still will be there. Okay, but as I said, we are taking n to be a lot large. Okay, now you will see that, okay, distance is kind of diminishing till 1000, I think. Yes, the second I make it for 10,000, see, it is actually on top of one another. The difference is not even considerable. The reason for that is exactly the same thing which I'm telling you, that the major point, and for 10,000, I think it was 10 to the power 5. Again, this is the kind of a graph which we get indistinguishable, right? So that's why we can say that whatever I'm getting for n square, that's the major thing which I need to take, right? So this was what I mean by this particular third point. We want to look for the largest factor in the runtime. Okay, so for example, if we have a nested loop, which we know that normally takes a larger time to run, okay, that will always have a greater time complexity than single loop, and thus that is the major point on which our time complexity will depend. To intuitively understand the same, you can also think that, let's say you have a group of 5 friends, okay, and you have to go somewhere together. Now it may happen that, let's say this particular, all of your friends are on time, okay, this particular person is 5 minutes late, but this person is 5 hours late. Now because of this person, all of you are going to get late, and this 5 minutes will not even have an effect. Now, even if it is 1 hour, you can extrapolate the same. That, let's say if we talk about in days, then if this person is making, let's say, 1 hour and the other person is taking 5 hours, if we extrapolate it, okay, so let's say from 1 hour, it will maybe become 5 hours, and from 5 hours, it will become 25 hours. So again, this difference will keep on increasing as I actually increase it to days or something, and it will not have an effect. So that's the same thing which is happening here. Your whole code, your whole group of friends is actually getting delayed because of that one person, one roadblock, and that has a major effect on when you will reach, when your program will stop working. Okay, so that's a very, very important thing to understand, everyone. Please make sure that you actually see the video again if you have any problem in this. The last point is that we want to express runtime, okay, runtime as input size, okay, as input size and we don't want to look for precision. What I mean by precision, I'm not actually interested in the exact time it's going to take, rather I cannot find that, but order of works. Okay, so if I know that okay, my input depends on the my runtime depends on the input as a quadratic, as a square, then that information is more than enough for me. Okay, that information will tell me. So for example, if it is 5n square and 5n cube, of course this will have a lot large effect, right? Plus I know that okay, how my graph is going to become. So it's going to be something like this here, and here it's going to be something like this, increasing a lot large in time. So if you are able to tell me that hey, your runtime depends on your input with this order, then that level of information is more than sufficient for me. I don't need to actually worry about basically understanding that okay, exactly what is the time, how precise I want to be. No, that is not my aim. I should just have an idea that okay, if my algorithm, the code which I have written, how that gets affected with respect to my input size. Okay, so these are the very important things to understand. Again, make sure that you see this whole notebook again so that you are able to revise. I have shown you visually as well that how this value has an effect, right? Why they are becoming same and why I am saying that this I can ignore. Okay, so I hope this thing is clear, everyone. Now let us actually kind of build more onto this intuition. Let's say now my bubble sort is having the equation something like this. So we saw that okay, it is kind of a quadratic part. We are going to prove that as well, should be fine. Something like this. Then of course I can say that this term is going to be the most dominant one. This term is going to be the most dominant term, and we are fine with most dominant term as well. With most dominant term, which in this case of course is going to be 20n square, right? Now again, I'm not saying that this is the exact relation. That will actually depend a lot on many factors. The way you are running it, what the implementation is, how and which PC you are running it. But I can be sure of one thing. Okay, this 20 might change to 18 tomorrow. Okay, it can change to even 1 tomorrow, but this n square will remain. That thing is always going to remain. That is not going to change, because when you actually increase your input, your overall runtime will depend somewhere on the input, and that is something using which we are going to find the time complexity. Okay, again, one thing you have to understand, this 20n square again is not the exact time. It is not the exact time which our algo is going to take. Okay, it will actually depend on the machine on which is working. So we don't have to again spread our head around this, that okay, what is the exact time going to be. This 20n square basically tells us the number of unit operations which are going to get performed. Because if you think once any algorithm, what it is doing is in the end, it is doing some unit operations, right? It is doing some operations. Now what I mean by unit operations, the unit operations are nothing but addition, subtraction, multiplication. These are the things which are happening, right? Comparison, all these are the different things, different operators which I am doing. And this particular relation tells me that hey, your unit operation seems to be actually in this way with respect to your input size. It is having this level of order with your input size. Okay, so now we have to see that using this whole understanding which we have built, can we actually come up with the time complexity somehow? Can we say that okay, how my time complexity is going to be? Again, as time changes a lot, we worry only about okay, this particular term. We are not worrying about this small things, right, everyone? So please make sure this again can change. And as I've shown you again, this overall thing, we will be majorly focusing on the n square part. We know that this n square is the part which is the relation of input with my time. This 20 can tomorrow change. You don't have to actually push yourself on this. This 20 can change tomorrow. So this is not something which I'm going to focus on. Okay. So cool, everyone. Now let us move forward. Just let me quickly summarize the few things which we have learned. So 3 major things, right? Again, all this I'm doing so that I can build your overall intuition and idea by showcasing you this visual thing. Then we are going to actually jump back and see how we can find. So first thing is we talk in terms of number of operations and not time, right? So that is what we have now come to, operation and not time, because number of operation, how much are taking place, that is kind of getting affected with the relation. We focus only on the highest power. And again, of course, with that, we don't care about the coefficient much. Don't care about coefficient much. So as of now, if you would see, what all we have done is we started with actually coming up with a relation. We worked an experimental analysis and saw many shortcomings in that, where we compared merge sort and quick sort. Then using that kind of analysis only, we actually find out that, hey, what kind of relation I'm getting, again, that can never give you the exact relation, that you can never find. But we were able to say that, hey, whatever you are getting, that is having this particular term, which is the most dominating term, which we also understood using this particular graph, right? So this graph helped us to understand that for large inputs, this kind of will be the most dominating term which you get. Okay. And again, all these 20n square or something, this can also change. It is dependent on your environment on which you are running, the PC which you are running. But we know that this n square is going to be the major part, right? So now let us understand about how we are going to quantify our time complexity. Okay, so for that we are going to use something known as big O complexity, right? That is going to help us to find the exact answer. So we will learn about this. Along with that, there are theta and omega, the few different more complexities which we are going to learn about. Till then, I want you all to make sure that you understand these things properly. I'm trying to build your intuition before actually introducing this big O complexity directly, because I think that is very, very much important in a topic like this, time complexity. Okay, cool then everyone, let's meet in the next video and we are going to learn about big O complexity. Thank you.